Okay, so welcome everybody to our first official short course of the fall semester. My name is Dylan, and today we're going to be going over HPRC's resources. So the slides that I'm presenting today were actually made by another staff member, Richard. Um, he made the slides. I'm doing the presentation. I'm a student worker at HPRC. I've been with them since I got to A&M in 2017. So I've watched them prop up Grace. I've watched them take down Ada. I've been around for and Curie. So I've been around for a lot of it. So I hope that today you guys learn a little bit about the resources we have, specifically Terra and Grace, and you guys can leave being a little bit more familiar with it. This afternoon short course is specifically about Slurm job scheduling. So I'm gonna touch on that a little bit in this course. But I'm mostly going to be going over like the environments on the clusters and the clusters themselves and kind of some high level stuff. The actual job submission, the detailed job submission short course will be this afternoon. I believe it's at 1:30. It's either 1 or 1:30. But this short course is going to run for 2.5 hours. The way we're going to kind of do it is I have a timer on my watch, which I'm about to start right now, for 50 minutes. So we're gonna go, I'm gonna talk for 50 minutes. We'll see how far we get, and then we'll take a 10-minute break. And then we'll come back, do another 50 minutes, take a 10-minute break, and then we'll finish out the course, whatever's left. I think that should work. 50 minutes is about as long as I can concentrate when someone's talking to me. So I feel that. I've been in a lot of courses this past 2 weeks, and the 50-minute talking and 10-minute break sort of works. I think really well. We also have some exercises that we'll be doing, so it'll be kind of interactive. Again, if you guys have questions, throw them in the chat. If you're in person, you have questions, raise your hand, and I'll, like, with my peripheral vision, find y'all. But yeah, without anything else, let's go ahead and get started. So the first thing is usage policies. Be a good compute citizen. So this is the standard stuff that you'll see every time you log into an A&M resource. Don't share your computer passwords. And don't use the clusters, don't use the supercomputers in a manner that violates US export control laws. So basically, if you're doing research that involves an international entity, you're probably gonna wanna run that by the export control office, because sometimes there can be a lot of laws and policies that you have to abide by. So if you're just doing research like for your class, you're 100% okay. But if you're doing research for an international group or something international, I would reach out to us, and we could reach out to the appropriate offices here at A&M. And also abide by the express or implied restrictions on using commercial software. So some licenses have restrictions on like where you can use them. So if you're using a software like that, and whenever you load it, on the computer, we will tell you, like, a notice comes up and says, hey, you're using this license, and this license stipulates XYZ. Just, yeah, follow the licensing rules, because if you don't, we could lose the license for everybody, and that wouldn't be nice. Okay, so some education resources before we get started. You could, if you don't have a basic knowledge of Linux commands, it's okay. The stuff that we're gonna do in this course is pretty simple. But if you would like to kind of learn more about Linux commands, we already had, I'm not sure if we're doing a Linux short course this year. We did have a Linux primer, and those videos can be found on our YouTube channel. So youtube.com, the channel is Texas A&M HPRC. Has videos from myself and other student technicians here. They put together a whole bunch of tutorials. I think that there's an introduction to Linux series on there. I know for sure the intro Linux primer is there, because I did that one. So you could find the primer and watch it there. Answers to frequently asked questions can be found in our wiki. And it's funny you can't see it, but I actually highlighted our wiki. That's weird. It doesn't show that it's highlighted on the projector, but whatever. Our wiki is a huge resource. When I first came to A&M in 2017, and I started working at HPRC, I was a sociology major, and I had like zero computing background. So all of my knowledge that I came from the wiki. I read the wiki a whole lot. I shadowed the workers at the time and just learned as much as I can. So if it seems daunting at first, I promise you it's not. If I could do it, anybody could do it. and the wiki is a great place to start. We're in the middle of transitioning our wiki to a more nicer or a nicer format, a more readable format. So right now it looks like a typical wiki, but in the coming days and hopefully like throughout the semester, we're going to be moving it to a nicer, kind of more user-friendly format, so you have a better experience there. But yeah, highly, highly recommend the wiki. You could find the wiki at hprc.tama.edu/wiki, and that'll take you to the main page. Okay, so follow along. The wiki has the exercises that we're gonna look into. The exercises are on Terra. So if you're taking the course, I'm assuming that you have an HPRC account already. So this means that you would have gone to hprc.tama.edu/apply and applied for an account. If you don't have an account and you're just kind of taking the course because you just want to see what resources we have, that's fine too. There's no it's not super important that you follow along. I'll be doing the exercises on my screen here, so you could follow along with me as I do them. They're just there in case you want to do them yourself. This is the actual path to the training directory. When we actually use them later on, there's a command that is going to use this path to copy them to your Scratch directory. If that doesn't make sense right now, hopefully it will when we get to that point. But yeah, this is just to tell you that the training examples are in Scratch training intro to Terra. And obviously, we're going to be using Terra to log in and kind of play around on. So if you do have a HPRC account, you can log into Terra. Typically, you log in with SSH from a terminal, but in the spirit of accessibility for everybody, these slides show you how to do it using the portal. So you can go to the portal by going to exit here, and I'm going to go to portal.hprc.tamu.edu. Portal.hprc.tamu.edu takes you to a page like this, and this is the this is our open on demand portal, so you could access the clusters from here. In this case, we're using Terra, so we click Terra. And normally it would bring me to a CAS login, so I have to log in with my net ID and my password. But I logged in earlier because I was like sending emails and stuff, so I'm already logged in Firefox. But this is what the portal looks like, the portal dashboard. You have to have an account with HPRC. It has to be current for this fiscal year. So if you haven't applied for an account for this fiscal year, you probably won't be able to get here. That's okay. I think that's basically it for the portal. To access the shell, the terminal, you go to this top banner right here where it says Files, Jobs, Clusters, and then Terra Shell Access. And this will open a shell in your browser, which you authenticate and log into Terra. Okay, and I'm in. Make it bigger. So yeah, logged into Terra there. You have to be on A&M Wi-Fi to connect to the clusters. So if you're on campus, you should be fine. I think there's a few buildings that have an issue connecting, but most of the time, if you're on College Station campus and Relic too, actually, I've not tried to connect from Relic. With Relic, you might need to use the VPN. But if you're on College Station campus, you should be fine. If you're working from somewhere else or you're off campus, like at your apartment or something, or a Starbucks, then you use the VPN. So you guys should know how to connect to the VPN by now. We've kind of been doing it for a while with COVID and stuff. So yeah. Okay. VPN if you're off campus. If you're on campus, the TAMU Wi-Fi is perfectly fine. Or if you have an office on campus, if you're hardwired in with the LAN drop, then you're fine as well. Yeah, we'll get to those in a second. So the clusters, these are the two big ones. On the left, we have Terra. Terra was deployed in 2017. I think its deployment actually like finished in, they put it up in 2016, and then in 2017, it was kind of like full scale deployment. It's a 320 node-ish cluster. That's an actual picture of it. It's in Teague. So if you guys know where Help Desk Central is, where they like help you with your IT stuff, your general IT questions, it's actually on the second or third floor above them. I forget. It's in the Teague data center. So like you go to Teague and if you have swipe access, you take the elevator on your left and then you go up and then there's a big data center room with like a fingerprint scanner and stuff. It's pretty cool. And then Terra is tucked away in the back. But that's what Terra looks like. It's a supercomputer, but it kind of looks a little small, right? It doesn't look too not too big. And on the right hand side, we have Grace. So Grace is our flagship cluster. We just deployed it, as in like just this year deployed it, finished deploying it. It's very big, 900 and something nodes. The exact number is on a slide in a few seconds, but Grace is the really big, cool one. It's got a lot of the CPUs are faster than the ones on Terra. It has 3 different kinds of GPUs right now. So we have a wide variety of GPUs, and each node has way more memory than the nodes on Terra. So if you're new to HPRC and you haven't really started, you'd probably want to go to Grace. Terra, being smaller, is also kind of more full at the moment. I was submitting jobs last night, and they were kind of pending for a long time because there's just far fewer nodes. But yeah, these are what they look like. This is what they look like. Grace has a cool white server rack aesthetic going on, and Grace is actually on the West Campus data center. So on West Campus, I've actually not been because I was gone. I was like working from home when COVID happened, so I didn't get to partake in the standing up of Grace, and I've actually yet to go see it. So I need to. I know who I need to track down, and I'm gonna track him down because I want to go see Grace in person. It's really cool. Okay, so the clusters are for you. What kind of problems are solved by clustered computing, by high performance computing? Well, a wide variety of them. But typically problems that are too big to fit on one laptop or workstation due to a limitation on memory, core count, or node count. Problems that scale well with more CPU cores or memory, single-threaded problems with millions of permutations, and problems that require high-speed storage and or interconnect. So basically the way a supercomputer works is a supercomputer is it's a bunch of smaller computers that are connected with really expensive interconnect. So if you think of your computer that you're on right now as one computer, if you were to hook up 10 of those computers together and then wire them so that they can all communicate with each other and share their resources, that's basically a supercomputer. That's a small scale supercomputer. That's the idea that these computers use. So each node on a supercomputer, you can kind of think of as an individual computer. It's an actual server like with a motherboard that has RAM slapped on it, CPUs, processors put on it, and in some cases accelerators, GPUs. And then there's different kinds of GPUs you could put on it, but each node is its own computer. And then we interconnect them with interconnect that is kind of like Ethernet, but more expensive and faster. And so that's a very, very simple way to kind of think of supercomputing. And then you could, if you're clever enough, you can write your code or have a program that kind of optimizes your code to be split up into many smaller problems. And those smaller problems are sent off to individual nodes or individual processes on each node. That smaller problem gets solved, and then it gets all pushed back into one main solution. So you take a big problem, you cut it down into a bunch of smaller, more manageable problems, and all of a sudden you have parallel computing. It's really clever, actually. So, okay, here's a very, very simple cluster diagram. We have 4 items here. We're gonna keep it really simple. So you have your login nodes. The login nodes are what you reach. So when I went to the portal and I hit Terra shell access and it had me log in, I connected to a login node. The login nodes are where you log in, kind of by their name. And you have access to the shared file storage. So you have access to all the files on the cluster. And you also have access to the job scheduler. The job scheduler, in the case of HPRC, it's going to be Slurm. Slurm stands for, well, okay, it used to be an acronym. It used to stand for Simple Linux Utility Resource Manager, I think. Is it simple? I can't remember if it's simple. I know it's Linux Utility Resource Manager. It used to be an acronym, now it's like a company. And it's basically, the job scheduler is a software that when we set it up, we tell Slurm, hey, this is the cluster that you're on. These are all the resources you have to work with. We set up partitions and queues and restrictions, and then we have people submit their jobs to the job scheduler, and the job scheduler finds places on the compute nodes for your job to run. That way, it's not like you have access to the entire computer at any given time. you only have access to the pieces that you request from the job scheduler. That lets us divide up the supercomputer so a bunch of different users can use it. It is a shared resource. And then, the shared file storage at the bottom is your hard drives. Basically, on the clusters, we're going to talk a little bit more about it, but there's basically two kinds of hard drives that you can think of: your home drive and then your scratch drive. And you can access that from the login node, so you could put your files there. And then the compute nodes also have access to that, obviously, so that they can do their work. Let me check the chat real quick. Yes, there we go. Simple, yeah, it's formerly known. I think it was used to be an acronym. Now it's like a Slurm workload manager. Yeah, fun fact. Okay, so a little bit more complex now. There's not just one login node, and there's not just one compute node, and then there's not just one type of compute nodes. So the login nodes are generally the same. They're going to be the same kinds of nodes. They typically have more memory than your average single compute node. That's because a lot of users are logging into them. But I believe Terra has 3 login nodes and Grace has 5. Which login node you land on doesn't really matter all too much, because they all have the same, they all are connected to the shared file storage system. So they all have your same home directory, your same scratch directory, that sort of thing. Sometimes there can be an issue, like you need to be on a specific login node for some reason. That's kind of a case-by-case thing. For most users, and it doesn't really matter where you log in, but you can tell where you log in from your prompt. So back to, I'm sorry, let me close some of these tabs real quick. Don't need all these. Okay, so I logged into Terra, remember? So I'm on login node 0301. So there's login node 0302 and 0303. So yeah, so that kind of tells me which login node I'm in. Again, it doesn't really matter. You just kind of got to understand in like the grand picture, in your picture, there's more than one login node. And then yeah, these login nodes talk to the job scheduler. I mentioned the job scheduler is Slurm. There are other kind of job schedulers out there. So if you ever leave HPRC and you go to another high performance computing center and they have high performance computers, you might see other job schedulers like LSF or PBS or Torque. Those are all the same general idea. They take in job files and then they sequester the resources for those jobs on the compute nodes and allocate those resources for you to run your job. Again, it's a very, very clever bit of programming that someone came up with a long time ago for using shared resources. And then, of course, there's hundreds of compute nodes with GPUs. There's big memory nodes. So the big memory nodes have like tons and tons of memory, because sometimes you need to store you need to store a lot of stuff in memory for some reason if your computation requires that. So we have nodes like that, etc. And then yeah, your file storage. Okay, so a little bit of an overview of the clusters themselves. Terra, like I said, Terra has 307 nodes. I thought it was closer to 320. Well, we'll go with this. So 307. So 307 nodes with 8,512 cores. So that seems like a whole lot until you look at Grace and you see, oh wow, Grace has 925 nodes with 44,000 cores. So yeah, Grace is really, really big. Most compute nodes on Terra have 28 cores and 64 gigabytes of memory. So think about your computer right now. I'm on a MacBook Pro and mine has 6 cores and 16 gigs of memory. So right off the bat, one core on Terra has 28, one node on Terra has 28 cores and 64 gigabytes of RAM. However, you would kind of think, oh wow, so what, one node on Terra is like 3 MacBook Pros? Not really. The power of supercomputer comes from many not as powerful computers. So each core can handle its own processes, but it's not necessarily faster than a single core on like a MacBook or any Windows machine. They typically are going to be a little slower because, like I said, their strength doesn't come from their speed; it comes from the fact that there's so many of them, and that's ideal for parallel computing. Same thing with the memory. Although I think the memory on Grace is actually like DDR4 or something like that. So it's pretty powerful. We have a question in the room. What's your question? The question in the room was what determines the power of the core, and that would be the generation of the core. So older cores are less efficient, and then their speed too. So it's basically the microarchitecture. So each year, the microarchitecture of the core gets smaller. I think right now Intel, they're all Intel cores. So I think Grace is, I don't even want to say. I think Grace is Skylake, or is it Cascade Lake? I'm not exactly sure, but it's basically they're all Intel cores, and the newer the generation, the more efficient each single CPU core is, and also the speed, like the frequency of the CPU. I don't know what gigahertz my laptop runs at, but I do know that the supercomputers they tend to have slower frequencies, because like I said, the speed is not so important. It's more the vast number of them. There's just so many. Good question though. Good question. Another question in the room.
So why did we decide to make Grace online since we
So the question was, why did we deploy Grace when we already have Terra? And the answer to that is, so typically HPC resources, they kind of have like a life cycle of like 4 years. It's kind of like you deploy it, and like 4 years later, the hardware of the system, it's kind of it's I don't want to say lacking, but yeah, like you see how fast computers how fast they change over time. So the Terra is still a fast computer, but for us to be competitive in like and offer top of the line resources, you have to deploy new clusters. So the CPUs and the infrastructure on Grace is newer, more efficient, and more powerful than the stuff that we have on Terra, because well, it's newer and it's newer architecture. I forget the exact generation of the CPUs, but it's okay. Yeah, Grace is Cascade Lake and Terra is Sky Lake, I want to say. So it's like a 4 generation. Is that a 4 generation difference? I forget. I know Sky Lake is like 6th gen, and Cascade is like at least 8th gen, I want to say. So it's a few generations newer, basically. Newer CPUs, more efficient, more powerful. And we want to offer the best. And we're a cutting edge university, so we have to offer really cutting edge stuff. So that's why we worked with Dell to deploy Grace. Terra is a Lenovo cluster. Typically, the clusters have like a computer manufacturer that like sponsors them. Terra is Lenovo. Grace is Dell. We also have other resources that we're not talking about today, but like Faster is also a Dell computer. Ada was an IBM computer, but we don't really work with IBM too much. We're mostly with Dell now. But good questions, guys. Good questions. So yeah, the features of the clusters. The GPUs are a big thing. So Terra's GPUs they're K80 NVIDIA K80 GPUs for the most part, and then there's also V100 Tesla V100 GPUs on Terra too. I believe there's 4 nodes. There are V100 nodes, but there's very few of them. The GPUs on Grace are really cool. Off the top of my head, they are RTX 6000s, A100s, and there's one other. I want to say, is it T4? Can't remember. I think there's a slide on it, but we have a bigger variety of GPUs on Grace. The reason I kind of don't include it is because like you don't really need to know the exact specific GPU that's on the cluster unless your resource really requires it. But our page here, hprc.tamil.edu/resources, goes in depth on like the generation of the CPU, their speed. You could like get the exact name of the CPU, and then go Google it on Intel and get all the information you need. But the job scheduler is Slurm on both. So we do that for continuity purposes and consistency. So if you understand how to use Terra, you immediately understand how to use Grace. That way, it keeps the learning curve as far down as we could possibly keep it. We want to make it. We want to make supercomputing as accessible as it can possibly be. Hence these courses and the primers and our help desk and stuff. So in in an effort towards that, we use the same job scheduler on both. And then, Terra's been online since 2017, and Grace has been online since this year. Oh, look, okay, yeah, this page talks about hardware. So for the specific hardware, you can go to our wiki, and then on our wiki sidebar, there's there's sections for like Grace and Terra, and then it has all the information. You can see the hardware summary. It breaks it down by nodes, as you can kind of see in this little snippet right here of Terra. It says the general 64 gigabyte compute, there's 256 of them, and then 48 nodes are 128 gigabyte compute nodes. So if you want a detailed look like that, go to our wiki and knock yourself out. Okay, getting started. Let's see. I got 25 minutes on my watch. So authentication and access. 3 steps to getting access to HPRC resources. The first one is getting an account. You get an account by going to hprc.tama.edu/apply and you apply. What do you need for an account? Well, first you got to be a student at A&M most of the time. Sometimes if you're not really a student at A&M and you're working on research that involves A&M in some way, you can get an account. Typically, the kind of the bar is having a net ID. So if you have a net ID and so you're affiliated with Texas A&M, you 9 times out of 10 will be able to get an account as long as you have some kind of research to do. The application is really simple. It just asks about, what you're going to be doing. So it gets some information from you. Are you a student? Is this for a class? What are you kind of doing? As a student, you apply for a basic account. Those typically get approved like in a day. So if you were to apply today, well, it'd be approved on Monday because today's Friday. But yeah, typically 1 business day. So once you get access, you'll get an email that says, hey, you have an account now, and it'll give you the SSH command to access. So if you want to access through SSH through your terminal, the command will be given to you. The command is literally right here. It's just SSH and then your net ID at terra.tama.edu or at grace.tama.edu. So my net ID is Dylan. So it would be SSH Dylan at terra.tama.edu. Also, of course, VPN to campus if you're not on campus. If you're on TAMU Wi-Fi, you're good to go. Duo is enabled, so yeah, you'll have to authenticate with Duo. This is what it looks like when you log in through a terminal. It says it gives you an option. Which option do you want to select? Push, a phone call, or whatever options you have available. I always go for push, so I just hit 1, and then my phone lights up, and I get myself in. If you need help with 2-factor, we have a wiki page for that. If you have a Duo key, you can actually use that, but that's more for like faculty, I guess. But yeah, you can use the Duo keys, the UBI keys, like the physical security stuff. You have that. Okay, so hands-on exercises. Activate the TAMU VPN and go to portal.hprc.tama.edu. So right now we're gonna get everybody to log in. If you don't want to follow along, you don't have to. And if you don't have an account, don't worry. It's not super difficult. But this first activity is literally just going to the portal and logging in. So I will close this. And in the spirit of starting from scratch, I will go along here. So portal.hprc.tamu.edu, and then click on Terra, and then pretend that I just logged in. And now I'm here. So I already talked about cluster access here, but the slides do want me to tell you that you could basically do everything from the portal. And I kind of actually recommend it if you're a new user to HPRC. If you need to upload files or download files, you do so from right here. You click files, and then it gives you access to your home directory or your scratch directory. So either place. Let's go to my scratch. So when I go to my scratch, I see all the files that are on Terra in my scratch area. And I can click this button up here to upload files from my local computer. So if I have some research data that my professor gave me on like a USB, plug it into my computer, and then upload it straight to Terra or Grace. This all works for Grace as well. And then I could download the files, I could remove them, stuff like that. Also from the portal, we can see our jobs. So we have our active jobs, we have a job composer, so you could create jobs if you don't want to actually write a job file. Shell access, we talked about that. And interactive apps. So if you're using an application that has a GUI, such as ANSYS, Abacus, MATLAB, ParaView, or you just want to start a general VNC session, you can go here. Let's say I'll just do let's do ANSYS. And when you click this, it brings you to this little job builder, and it says, okay, what version of ANSYS do you want to use? How long do you want this job to run for? How many cores do you want this job to have access to? And how much memory do you want this job to use? And then GPU, I think it'll all GPU, yeah. And then when you launch this job, it'll actually create, well, first it'll go into queue and it'll be pending for a second because it's waiting for the resources to become available for you. Once the resources are available, you'll be able to click launch and it's going to open up a new window. It's going to open up a new window with a virtual terminal on Terra as if you're kind of sitting there plugged into Terra. It's going to be in your browser and you'll have access to the terminal if you want to use the terminal, but it will automatically launch whatever application that you told it to launch. So in this case, this would launch ANSYS Workbench version 0.2.0, aka ANSYS 2020 R1. So yeah, so if you're using a software that has a GUI and you kind of want to use it like that, going through the portal is going to be a great tool for you. The limitations here are that with the portal, you're limited to one node, so you can't do a parallel job here. So you're restricted to the hardware limits of a single node. Remember, on Terra, each node has 28 cores. Most of them have 64 gigs of memory, but there are some nodes that have 128 gigabytes of memory, so you'll have access to a little bit more. But if you need more cores or more memory, then you'll have to split your job up and run it parallel. And the only way to do that is using the scheduler. So you'd have to write a job file. And we will go over that shortly. Oh, also the dashboard. Yeah, let me give a quick shout out to the dashboard because it's really cool. This little item right here next to interactive apps, you click here, go to Terra dashboard. Here's where you can, you'll see your account. So I can see which allocations I have. So I have 2 allocations here. I can set them as my default. I could see the node utilization. So I could see what's going on Terra right now. Allocated, mixed, and idle. So it looks like there's very few nodes that are idle, 23. But there's quite a few CPUs that are idle. So if you had to run a job, now would be the time to do it. I could see the utilization of my disk quota. So I could see my home drive and my scratch drive. I could see how much data is in there and how much of my limit I've used. And I can request quota increases. This is kind of the preferred way of submitting quota increases. I'm going to go over that in a few slides. But just to kind of show you guys, this dashboard is really good for just your basic cluster monitoring. It's also available on Grace. Same idea, you just go to portal.hprc.tama.edu, go to Grace, and then go to Grace dashboard. Shout out to the technicians who worked on that because that looks really nice. Okay, back to the slides. Okay, so I just talked about quotas. So now's a perfect time to introduce a slide that talks about quotas. So the shared file storage system has 2 drives. It has your home drive and your scratch drive. Your home is available at /home/user, where user is a variable for your NetID, aka your username. So whenever you log into the cluster, you always use your NetID. And so your NetID is going to be your username. They're going to be interchangeable. You might hear me say one or the other, but 9 times out of 10, I'd say like 99 times out of 100, actually, your NetID is your username. So /home/NetID is where you're going to land. That specific area has a limit of 10 gigabytes or 10,000 files. The reason it has that limit is because we back up your homes nightly, and we have thousands of users. So thousands of users times 10 gigabytes is a big number. And in order to back up everybody's drive, we have to kind of restrict that to 10 gigs and 10,000 files. We've never issued an increase for anyone's home as far as I've been here for that reason. So if you need to store lots of files, you're going to put them in your scratch directory. Also, I should mention that these quotas are, it's one or the other. So if you have 1 gigabyte of files, but you have 10,001 really small files, you're still going to hit that limit. It's not a combined thing. It's you either hit one or the other. Whichever one you hit first is going to stop you. And the error you're going to get is called disk quota exceeded. So yeah, we don't increase your home. We do, and on some occasions, increase your scratch. So if you're doing research and you have a valid reason, you can submit a quota increase request. Typically, we ask now that you do that through the portal, through the dashboard. So right here, boom, click this button, and it's going to ask you some questions. Those questions are designed to kind of figure out, what research are you doing, and it helps us have the questions that we need so we could make a decision on that increase. Nowadays, the increases typically last for 6 months, and most of them are less than 10 terabytes. So we see, 1 terabyte is kind of a small amount of data when it comes to like HPC problems. So we understand that, and we want, again, these computers to be accessible to people. So if you guys need more space than 1 terabyte or 250,000 files, reach out either through an email to help@hprc.tama.edu, our normal email address, or go through the Terra toolbox, the dashboard, and send in a quota increase. We'll get back to you, and I think typically most of them are granted, but they are temporary and they'll last for 6 months. We have a question in the room.
So would there be a quick demo of how to run a piece of code using the
Yeah. So the question was, will there be a demo on how to run a piece of code on HPRC later? And yes, it's towards the end. The examples, like the training materials, have example job files that I'll go over in depth, and it shows you you write a job file, you specify the resources you want, and then at the very bottom you put the code in that you want it to run, and then it'll execute that. But that's in like section 2 or 3. But yeah. Okay. So still on file systems and user directories, to show your quota. First off, you could see your quota from the dashboard, but from the terminal, I don't have a terminal open. Let me log in real quick. Log in. Okay. Okay. So I'm logged into Terra, and to show my quota, I can say show quota, just like this, and this is going to print out that exact same output that we saw. We see the limit of 10 gigabytes and the current usage. So if you're downloading or uploading a lot of files to Terra or Grace, and you think you might hit that quota, show quota is the command to use. We had a question in chat. Okay, I'm not sure if I missed this, but I remember in Ada we also had a directory for storage. Do we have that in Terra or Grace? Good question. So no, that's exactly right. So what he's referring to is the tiered directory, also known as the archive on Ada. The new clusters do not have tiered. So good question. If you guys are a user that used Ada before, you'll know that Ada had 3 drives, had Scratch, Home, and Tiered. We don't have Tiered anymore. Tiered was unique to Ada. So you're on Grace and Terra, you only have your Home and your Scratch. So good question, yeah, and good catch too. It's good to see a returning user. That's really cool. Okay. Oh yeah, see, so this right here says do not share your Home, Scratch, or Tiered directories. Tiered is only on Ada. So I thought I scrubbed all that stuff, but missed a little piece there. Okay. Let's upload a file. So hands-on exercise, upload a file in Terra. So let's pretend that, let's see, how much time do we have? We have 12 minutes. Let's pretend that we're gonna do some research, and we need to upload a file. I'm blanking on what we need to, let's say we need to upload a picture of a bird or something, because we're doing machine learning on birds. So the quickest, easiest way to do that is from my browser, portal, HPRC.tama.edu, go to Terra or Grace if you're using Grace, and then files. And remember, I want to put my stuff in my Scratch directory, because Scratch has way more room than my Home. So I'd come here, and then I'd go to upload, and then I'd click browse, and I'd find a file somewhere. this cat nod. This is the cat that nods. If you guys seen that, I'm not gonna put that on Terra, but you get the idea. You'd click open and it would upload it. So you can also do that with directories. So you could just put a whole bunch of files up there real quick. It's by far the easiest way. You could download third-party applications called SFTP applications that will do this. If you're familiar with WinSCP, that's an example of an SFTP application for Windows. FileZilla is one, CyberDuck is one. But uploading stuff, if you're a new user, go to the portal, go to files and put it up there. I think you can actually just drag and drop from like File Explorer here too. Works really, really well. Okay. And check your file quota. So we just went over this, so I'm not gonna make y'all do it. But remember, there's two ways to do it. From the terminal, show quota, really simple command, or go to the portal and then go to the dashboard and find your quota there. Really, really good. Okay. Now we've got 10 minutes and we're gonna start software infrastructure. Let's see what these coming up slides are. Okay, we could do a few of these. So software. So there's tons of software on the cluster, and there's many different versions of software on the cluster. We provide both pre-installed software and software installation assistance. Software wiki pages provide instructions and examples for specific software. So if you're using a software that a ton of people use, there's probably a wiki page on it, and it probably has instructions on the commands that you would need to run that specific software. So I would, again, direct you to the wiki. If you're using ANSYS, I would say go to the wiki and then Google or search ANSYS. And then you'll find wiki pages on ANSYS with job files that describe how to actually use ANSYS on the cluster. There's also license restricted software. This license restricted software, there's basically two types. There's license restricted software that is restricted, but the licenses are available for everybody. Those come on a first come, first serve. And then there's license restricted software that is only available to people in that research group. You have a question? Oh, is there another question in the chat? The hand up. How can I see people's reactions? Gotcha. Oh, Edwin, did you still have a question, or was that, I think I answered your question about tiered. Is that right? Ooh. Okay, we actually have some more questions in the chat too. So a person says, my login looks like user at Terra 3, and then a little squiggly. And before disconnecting during test, I was at user at Terra 2 on current login. I see a different directory created, which I did not create. No problem, Edwin, don't worry about it. So to answer your question, Shalini, so yeah, user at Terra 3. Terra 3 is that login node. So again, like you're connected to the Terra 3 login node. And then when you logged out and you reconnected, looks like you connected to Terra 2, which is a different login node. Sometimes when you log out of your shell, you like close the connection. There's a lot of configuration that happens. For example, all the commands that you enter in your shell get saved to your bash history. And your bash history gets written every time you close the connection. So whenever you close you log out, or you like actually physically press the X button on your little shell, bash, which is kind of like the framework that you're using, it can create files and do stuff like that. So I wouldn't be too surprised if something like that happens, because like, for example, every time you log out, it writes to your bash history. You probably won't, like, you shouldn't see different files. For example, if I made a file called Dylan's homework on Terra 3 and I logged out and then logged back in and I was on Terra 2, I would still see that file Dylan's homework there in my home. So yeah. For the exercises, will you go over the parallel computation using the other nodes or cores? And the answer to that is yes. The exercises later on show examples on how to submit single node jobs and how to submit multi-node jobs. So multiple computers running in parallel to solve your problems. It basically comes down to the parameters that you feed Slurm, and then Slurm kind of understands like where to put your jobs and stuff like that. But yeah, we do have examples of that later on. Sorry, that's kind of towards the end of the class. And again, like the Slurm specific stuff we'll go over in much more detail this afternoon. I actually think Lisa, who's in the chat right now, she will be teaching that course. That's a really good course too. That's like the deep dive on Slurm and that specific stuff. But yeah, good questions. Thank you for the questions, guys. Okay, yeah, so software. The gist of this is there's lots of software on the clusters. It's a lot of it's already pre-installed. If you're using some kind of niche software that we haven't installed yet, send us an email. We can help you install it, or you could try to install it yourself. There's nothing wrong with installing it yourself. You're probably gonna want to install it in your Scratch because there's much more space there. Software installation can be difficult at best. So you might need some help. If you want us to do it for you, you can request that we do it. It's going to take a little while because we do have a software request queue, and like I said, it kind of takes a while to install the software and then document the steps and then package that off and send it to you. We could help you install it in your own Scratch directory, which is kind of what I just described, or you could ask us to install it as a module. We're going to talk about modules in a second, which if you install the software as a module, that's going to take longer, but it's going to be available to everybody. So like maybe you're in a research group and you want everyone to have access to the software. So you would ask us to install it as a module. We'd put it there and then you'd be able to load it. Your students would be able, your other like teammates would be able to load it, and your professor would be able to load it. Don't run the sudo command. The sudo command is in Linux, the administrator command. It's the super user command. You shouldn't be able to run it because you won't have admin privileges. And if you try to run the sudo command, you'll get a bunch of messages that say, hey, you shouldn't do this. But if you do it anyway, which I've done, you get a message that says that we've been notified, and it emails all the admins and says, hey, this person ignored the warnings and still tried to run sudo. It's not going to do anything. It'll just send us an email, and then we'll have to message you and say, hey, why'd you ignore the messages? Don't do that. So don't use sudo. It's not like you can anyway, but just kind of don't try it. If you're doing a software installation that you think requires sudo, send us an email. Sometimes we can get around that. Sometimes we can't. So yeah, I would suggest kind of go as far as you can go, and then send us an email and we'll work with you. Okay. Do I have time to talk about computing environment? I think right now is a good time to break because computing environment is going to get a little bit dense. So it is 10:50 right now. Let's take a break and reconvene at 11. So we have a 10-minute quick little break. If you're on Zoom, feel free to stand up and stretch your legs. I'm going to keep on sitting down, but yeah, we will reconvene at 11 a.m. Central Daylight Time. Oh, and if you have questions, throw them in the chat. I will be here. Okay, everybody, I hope you guys had a good break. I took a few sips of water, so my voice isn't so hoarse. But we can go ahead and continue. I was showing the people in person our YouTube channel, which again, I will highlight because I'm on there a few times, and we're at 380 subscribers. So yeah, if you guys, we also had a question in the chat of whether or not the recording will be available. Yes, it will be. Like I said, it just takes a little while because we have to, we kind of cut out the parts where we do these kind of sidebars, and then we have to transcribe them, and that's what takes the longest. But Texas A&M HPRC, go there and subscribe. We're almost at 400 subscribers. I'll save you the normal YouTube spiel, but yeah. Okay, back to Firefox and to my slides. So when we left off, we were talking about the computing environment, specifically the path. So if you're new to Linux, you might say, what's the path? Am I sharing my screen? Okay, great. The path is the location on disk where an executable or library may be found. So what's an executable? An executable is, well, the file that actually runs stuff. So right now I'm in Firefox. So there's a Firefox executable somewhere on this MacBook. I think this specific executable is in like user applications or something like that. In Linux, the executables are typically inside of bin. Um, uh, but the way we manage it is because we have so many different versions of software, we have a system in place called the module system, which lets you choose which software you want to add to your path. When you add that software to your path, it becomes available for you to call, for you to type into the terminal and access. So paths are saved as environment variables, so you could choose which libraries and executables you want which ones you want to use while you're working, and you can change that by modifying the variables. There's a lot of software, many versions, and many paths to manage. So how do we manage all of these versions? Well, it's with the LMOD system. So it's called the LMOD system, but the way you interact with it is actually called module. So LMOD system, module system, same deal. It all deals with the user, you, selecting the software that you want and then the version of the software. Each version of a software or application or library is available as a module, and modules have a format. So the format that we use is the first part is the software name, obviously. So in this case, we see Top Hat slash the version of the software. So this is Top Hat version 2.1.1, and then the tool chain. The tool chain is the collection of compilers and libraries that was used to build the software. So obviously, when you compile software, you have to have a compiler. And then there's different kinds of compilers. There's Intel compilers, which are compilers that are optimized by Intel and then licensed out to people. So we have a university-wide, is it university-wide, division-wide, organization-wide? We have a license for it, so everybody can use the Intel compilers. And then we throw those compilers with libraries that the compiler uses, and we get a tool chain. So a tool chain is, again, a sort of an HPRC creation, but just think of it as your compiler groups. So this specific example is Top Hat version 2.1.1, built and compiled with the Intel 2017A toolchain / compiler group, and then the dependency version. So this specific Top Hat needs Python 2.7 to work. You might not see a dependency version. Sometimes you will, sometimes you won't. Most of the time, you will always see the software name and the version. And then you might see the toolchain. If it can be built with multiple toolchains, then we build all the versions of it with the different toolchains, and then maybe the dependency. And when you use the module system, module changes your path, so it messes with that environment variable, and it adds the path to this executable to your path. And then you can just say Top Hat from the command line, and Terra will launch Top Hat for you. So module usage basics on Terra. The actual commands to interact with the module system. Module avail or MLA will list all available modules. Sometimes it's very slow. And then you use the spacebar or the page up and down to go up and down. You also go up and down with the arrow keys, Q to quit. So let's go to the terminal. I'm going to Control L to clear my screen. Now I'm logged into Terra, remember, and I'm going to say module avail. And you can, when I enter the command, I don't get an immediate error. And that's because it's going through all the modules. There's a lot of them. So we're not going to wait for this to finish unless it finishes like really soon, like now. No. Okay. So it's going to go through all and list every single version that's available, every single module. So every software and the versions of those software that's available. That's a very, very broad search. If you, oh, look, it just finished. Look at that. So here's all the modules that are available. So I could load any of these. So let's say I wanted to load, let's go with MATLAB 2021A. I'm going to copy this. So I have this on my clipboard, and I'm going to hit Q to get my little prompt back down here so I could type in commands again. Now, let's say I want to do some MATLAB work. I haven't loaded MATLAB. I've just logged into Terra. If I say MATLAB, nothing happens. Bash, which is the shell that I'm connected to, says Bash says, you said MATLAB, and the error that we're getting is command not found. I don't know what MATLAB means. So what we can do is say module load, and then I'm pasting the name of the module. So I got the name of the module right here, and I hit enter. It takes a second. It takes a second, okay. And now if I say MATLAB, all of a sudden, now it knows what MATLAB is. And it's starting MATLAB from host, Terra login 0301. And yeah, it's running. It's gonna try to actually run MATLAB. I'm gonna hit Control C to stop it. But that's the idea. We have tons of different software and then tons of different versions of those different versions of software. So it gets really confusing really quickly, which is why we use the module system. Module avail shows you all the available software. Module spider is a specific search. So, okay, I'm using MATLAB. Maybe I want to use an older version of MATLAB. I can say module spider MATLAB, and it returns quicker than module avail all the versions of MATLAB that are available. So I see we have versions of MATLAB from 2016 all the way up to 2021A, and then I can do the same thing, hitting Q to get my little prompt back, and then I'm gonna highlight MATLAB 2016. I'm gonna Control C to copy this, but before I load another version of MATLAB, I want to clear I want to clear the modules I have currently listed. I'm gonna say module list, which shows me which modules I currently have listed, loaded. I see I have MATLAB 2021. I don't want that. I want the older version because I'm retro, and that's just kind of how I am. So I'm gonna say module purge. Module purge removes all the modules you have loaded. Once again, module list, nothing's there. So now module load, MATLAB 2016. Takes a second. Takes a second. And it's there. Okay. And then I get this nice little message that says, hey, MATLAB versions 2016, 17, and 17b have been deprecated and are scheduled to be removed. Looks like they haven't been removed yet, but yeah. So if you load modules that have some kind of issues with them, typically you'll see a message like this that says, hey, something's going on. But yeah, that's the idea with the module system. Now, that's how the module system works on Terra. The same thing exists on Grace with one slight difference. On Grace, installed applications are made available with the module system. However, they use a software hierarchy inside the module system. So what does that mean? That means that I mentioned that the software has dependencies in some cases. So let's go to, let's log into, open a new tab, log in. I should do this. SSH Dylan at grace.tamu.edu. So that connects me to Grace. I log in. I type my password in wrong. Okay. Now I authenticate. All right. So now that I'm in Grace, Grace, like I said, works the same way with the module system as Terra, except one difference: it's a hierarchical system. So instead of searching for the modules that you want immediately, you first start by loading the compiler, aka the toolchain that the software is built with. So I'm gonna say module avail, and I see all the software that I could load that either doesn't need a compiler toolchain or is the compiler toolchain. So I see GCC 9.3.0. GCC, if anyone's familiar with it, is the GNU compiler collection. It's an open source collection of compilers. So I'm gonna go ahead and load that one. So I hit Control C and then Q, module load GCC 9.3.0. So now I have at the very bottom, I have a tool chain loaded. So I have a collection of compilers and libraries in my module list: GCC core, zlib, bin utils, and GCC 9.3. So if I do module avail again, now there's different software that I could load. This software is our software applications that were built with this compiler. So I know that anything that I load from right here is going to be compatible. I don't have to worry about the compatibility anymore because we've taken that off. So I could also load CUDA 11. I could load Bowtie. I could load, I think there was an example. Yak. I'm not sure what Yak is. But yeah, the idea on Grace is that you use the module system, but you start from the very bottom. First, you load the compilers and the toolchains that the software was built with, and then you load the software itself. This reduces the chance of there being an incompatible library or compiler, because those errors can be annoying to track down once you start running your job. So in order to eliminate that, we implemented the hierarchical system. So key takeaway on Grace, start by loading the compiler. Don't update right now. On Grace, start by loading the compiler. You could view the available compilers with module avail, and then you module load them the same way. Module avail again, and you'll see what's now available after you have this compiler in. And then you could load whatever software you want to use. That's the key takeaway. Okay, so we have an exercise here. This goes over module usage basics. This exercise, I think we can skip this because I kind of want to spend more time on the actual job submissions because that's where kind of the questions are coming from. But this exercise is basically just how you load, you module load, you can module avail, module load again. But again, the takeaways from the module system: module avail shows you everything that's available. Module spider shows you specific packages that you give it. So you say module spider MATLAB, it'll show you what we have with MATLAB. And then module load, whatever you want to use. When you're done, module purge, it removes it. I will say, every time you log into the clusters, you have to module load again. So I loaded MATLAB. If I log out of my cluster, I close my terminal, I go to lunch, I come back, I've logged out. When I log back in again, I'll have to load MATLAB once again. You want to avoid automatically loading modules because that can cause a lot of issues too. So it can be tedious, but trust me, it's worth not having that headache later on. So always load your modules whenever you log in. Yeah, you have to kind of recreate that environment. Okay, development environment, toolchains. I kind of already talked about these, but toolchains are combinations of compilers, message passing interface libraries, and highly optimized math libraries. Toolchain components are primarily either Intel or open source. So most of the time we either have the GCC compilers, which I said are the open source ones, and then the Intel compilers, which are the licensed Intel compilers. You can see them when you do the module system, you'll find them just like that. Again, on Grace, you're gonna module avail, and on Terra, you'll just say module spider and you can search them directly. We have a wiki page, hprc.tama.edu/wiki, software toolchains, that goes very in depth on all the compilers and all the libraries that we have. This is like a little snippet of that table. It talks about which toolchain is open source, which one is Intel, and which one has mixed items from both. Example usage of loading the toolchain. It's exactly like loading a module. You module spider for that toolchain, and then you module load whatever version you want. You just copy and paste it. Okay, module usage practices. Applications installed as modules are available to all users except for restricted modules. The restricted modules are the ones that I mentioned that have licenses on them. So sometimes specific software has a license that is restricted to only like this one specific research group who pays for it. In those cases, it's installed as a module. You just won't be able to see it because you're not part of that group. If you want access to that module, then you'd have to reach out to the person who pays for the license, who's typically the faculty in charge of that group. And then that faculty member will email us and say, yes, give Dylan access to my Gaussian license or whatever. And then we'd put you in the group and you'd have access to it. It's a good habit to unload unused modules before loading new modules. Get in the habit of module purging. That's going to reduce some issues that's going to reduce the issues that you're going to see from mixing your modules together. Sometimes the module system will tell you, hey, you've loaded two modules that could be incompatible. I wouldn't rely on it though. You kind of just want to be purging each time. And then this is what I said, don't load modules in your bash RC. That would make them load automatically. We don't want to do that because that can cause a lot of issues. Just kind of don't do that. Avoid mixing toolchains when working, avoid mixing toolchains when loading multiple modules at the same time. That is basically completely eliminated with Grace. However, on Terra that still stands. If you're using software that is built with Intel, you kind of want to, you're kind of going to want to stick to Intel on that one. You're even going to want to stick to the same Intel from that same year. So like Intel 2018A, you're going to want to stick with Intel 2018A for all the modules that you load there. I believe on Grace, we've virtually eliminated that issue with a hierarchical system, but mixing toolchains like that can cause frustrating headaches and issues. Okay, so a software install example, virtual environment. So Python is a language that supports many external libraries in the form of extensions called Python packages. So if you guys are familiar with Python, you're probably familiar with Python packages. I think we had a question about a Python package like over the break in a Jupyter notebook. But when you're using Python on our clusters, there are some commonly used packages that we already have installed as modules, but most of the time, what you'll want to do is create your own virtual environment. So I'm going to show you guys how to do that real quick. This is another good example. So the virtual environment feature lets you create your own little setup where you can, where you're basically the administrator of your own little Python environment. This lets you install whatever combination of packages you need for your specific problem, and then you could save that environment, or you could delete it and stuff like that. So let's go ahead and do this. Make this full screen so everyone can see it real big. Open my terminal, and we're gonna go to run Terra. So I'm gonna close this one. Control L to clear my screen. Now I'm gonna CD to my Scratch, because since I'm doing some actual work, I want to be in my Scratch. And first I need to make a directory and call it Python example. So mkdir Python example makes a folder called Python example. And now I'm gonna CD to move into it. And I hit PY and tab, and it auto computes for me. Again, if you guys want to follow along, you can. You don't have to. I just kind of want to show you how this works. Okay, so now I'm gonna module purge, because that's best practice. Make sure I have no modules right now. And see, this wants me to load Python. Oops. Module load Python 3.6.6 dash Intel 2018B. So if you are following along from kind of the syntax that we were using and the format, this is Python version 3.6.6 with the Intel 2018B compiler collection / toolchain. Hit enter. Okay, so now I'm going to say Python. Actually, I'm going to say, now I have Python 3 loaded now, so I'm going to say virtual env, and then what's the name of the environment? My underscore example underscore env. It's actually a virtual environment, so we'll say venv. Yeah. So what this is doing is this is creating my own area of Python where I can install my own packages. So now I'll be the administrator of this area called my example. That lets me really customize the packages that I have and that I'm going to use. So let's say I specifically want like, I don't know, a very specific version of TensorFlow. I could install that there. So now that it's created, it used this version of Python, and it created the environment inside my Scratch. I can see it right here. Now to activate it, I say source my example env /bin/activate. When I do that, I see this little parentheses over here, and this tells me now I'm inside a virtual environment. So I can run pip to like the Python repository command, and I can install packages inside here. So if I do Python -c import import PyTime, yeah. I get an error that says, hey, we don't have a module called PyTime. So if I do pip install Python-time, now I can install, oh, I misspelled install. I can install this this package into my environment. If I tried to pip install something while not in a virtual environment, basically what that's trying to do is that's trying to install it for everybody on the cluster. You'd obviously need admin access to do that. So you'd get a permission denied error. And then if you tried to run sudo pip install, that's when you run into the issue where it notifies us. So yeah, that's why I mentioned, yeah, if you're gonna install stuff, you typically don't need to use sudo. There's always workarounds like that. So now we've installed PyTime. If I go here and say Python -c import PyTime, it works. I don't get an error. So that's just a quick demonstration specifically with Python because a lot of people use Python. If you want to use specific environments for Python, use virtual environments. There's also a lot of, we have guides on this on our wiki. But yeah, you would take it from here and pip install all of your specific packages and software. You want to do this inside your Scratch because virtual environments they create a lot of files. They create tons of small files. So you'd very, 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 very quickly hit your 10,000 file limit in your home. So virtual environments are going to go in your Scratch. And then to leave, we say deactivate. And now I'm back. Okay, now the moment you've all been waiting for, cluster computing. So actually submitting jobs to the cluster. Batch computing on HPRC resources. So batch computing starts with a batch job script, aka a job script file, aka a job file. A job script file is a text file that contains both Unix commands and batch manager job parameters. So the batch manager is Slurm, aka the job scheduler. And this is a little diagram of how that works. On the login node, you create a job. That job takes the form of a job script file. You submit that job script file to the batch manager, and the batch manager reads the output of that, it reads that file, and it reads it for two things. The first thing are the directives, which are lines that begin with sbatch. We're gonna see those in just a second, and that's, Slurm is gonna read those, recognize those, and allocate resources for your job based on what you tell it. And then once it has found those resources and reserved them for you, it's gonna take your job script, move it to those compute nodes where your resources are, and then run the Unix commands that are listed beneath the batch job parameters on those nodes as if you've typed them in. So the idea is the Unix commands that you enter under the batch job parameters are the same commands that you would enter onto your terminal yourself. The job script file just copies those commands and runs them on your behalf on a compute node somewhere, non-interactively. So before we submit jobs, you have to understand what consumable computing resources are. Resources specified in a job file are the processor cores, so how many CPUs you want to use, how much memory you want your job to have access to, the wall time, and whether or not you want a GPU or not. A service unit, service units are tied to your billing accounts. So when you apply for access, again, as a student, you apply for a basic account. That gives you login access to the cluster, so you can log into Grace and Terra, and you also get a basic allocation of 5,000 SUs. What is an SU? Well, there's a math formula behind it, but typically you can kind of think of it as 1 core or 2 gigabytes of memory for 1 hour. So a 1 core job for 1 hour with 2 gigs of memory is going to cost you 1 SU. A 1 core job with 4 gigabytes will cost you, for 1 hour, will cost you 2 SUs. And it goes like that. So if you want a really, really simple, really, really quick and dirty estimate, think cores per hour, and then tie memory into that somehow. The exact formula is on our wiki right there, HPRC AMS service unit. if you're so inclined to go figure out like a very specific calculation, you could go there and find the actual formula. So how do you view how many SUs you have? That's going to be the my project command. We have a question in the room. Yes, so the question was, SUs are different from Grace and Terra. Yes, so your SUs are exclusive to the cluster that you get them on. When you apply for a basic, you get 5,000 on Grace, 5,000 on Terra. You can't send them between each other. So you got once you run out, yeah. Oh yeah, yeah. So the question was like the memory per hour is different. So I see what you're saying. And like Terra has less memory on each node than Grace does, but you specify how much memory you want to use in your job file, and it's that item that you specified that gets charged. So like on Terra, you could say I want to use 20 gigs of memory for 1 hour. You could also say that on Grace, you're going to get charged the same because it's 2 gigs of memory, or it's the same amount of memory, even though there's different amounts of it available. So we're really like dividing up each node. So on Terra, you have 64 gigs of memory that is available to you. You're going to be charged the 20 gigabytes of memory that you request. Am I just confusing you even more? I'm sorry. Okay. Sorry. So yeah, service units, 1 core for 1 hour or 2 gigs of memory for 1 hour. And you specify how much memory and how many cores in the actual job file you want to use in the job file. Okay, another consumable computing resource are license tokens. So I mentioned that we host, there's some software that has licenses that's available to everybody. That's what this is referring to here. The example that we always go to is ANSYS. ANSYS is a licensed software, but we host the licenses for it. They're a first come, first serve kind of thing. So when you launch an ANSYS job, it automatically checks out a license for you. If there's no licenses available when you run your job, you're going to get an error that says no licenses available. We typically don't run out of licenses unless we're getting to like crunch time, to the end of a semester, or when something, when a big deadline is coming up. It's like typically the end of the semester, the end of the summer, those sorts of like when you sort of expect everyone to be kind of rushing for their work at the same time. We have a license status checker tool. It's called license_status that you can run that shows you all the available licenses that are available and how many are issued, how many are in use, and that sort of thing. It's nice and color-coded, and it was written by a student who graduated. I think it was written by Crystal, but it's a very nice tool. So you call it by saying license_status, exactly like that. I'll show you. So Control L to clear my screen. License _status, and then it says, okay, we need an option. Let's just say -A, and this gives me all the licenses that are available. So as you can see, there's a whole bunch of licenses, and oh, look at that. So MOE, whatever that is, has 3 licenses total, and all 3 are in use. So I hope you don't have to run an MOE job right now. Not that I know what that is at all, but okay. So -H gives you the help option for that. Okay, so Slurm. Examples of SUs charged based on job cores, time, and memory requested. Like I said, a service unit on Grace and Terra is equivalent to 1 core or 2 gigabytes of memory usage for 1 hour. So if you're asking for 1 core, 2 gigs of memory for 1 hour, you're going to be charged 1 SU. I think I kind of said this already inadvertently. 1 core, 56 gigs of memory for 1 hour is 28 SUs. This is just kind of illustrating what I mentioned earlier. I'm going to hammer that in one more time. 1 core for 1 hour or 2 gigs of memory for 1 hour. So large jobs that use tons of cores and lots of memory for many hours, this SU charge can start going through the roof. And then I think I have a slide. Okay, in case I don't have a slide, I'll talk about what happens when you run out of SUs. So if you submit a job and you don't have enough SUs to cover it, As a student, remember you had an allocation of 5,000 SUs. Now, 5,000 goes by pretty quickly, especially with the larger jobs, like I said. So when you exceed your 5,000, what you need to do is have your professor, your whoever you're working with, your advisor, your professor, whoever it is that is kind of sponsoring the research that you're doing, they will apply for an account on your behalf. It's called a startup account. So they apply for an account, and that startup allocation is given 200,000 SUs, a little bit more than the 5,000 that you're given. And the key difference between the startup and the basic account is that the startup account can sub-allocate SUs. So they can list you as a researcher and say, let's say that Chris is my professor, and I said, Chris, I ran out of SUs, I need more. He can go and list me as a researcher, and then he can sub-allocate SUs from his 200,000 that he was given to me. So as a student, you're only given an allocation of 5,000. It's your professor who will go beyond that, get the 200,000, and then ask us to send you SUs from their account. So that's what happens when you run out of SUs. If you run out of those 200,000, they can apply for another 200,000. And if they still exceed that, then they can apply for one more allocation, which is called a research. And that one starts at 2 million SUs. But we won't really go into that because that takes a little bit more to explain. We will go into batch queues. Batch queues, so when you submit your job, the job is auto-assigned to batch queues based on the resources requested. So again, it's looking at the number of cores and how many nodes you want to use and the wall time limit. It takes that information and it puts your job into a queue, just so we have dedicated node groups that are for people who want to run really long jobs. Maybe your job is really short and it's just going to run for like 1 hour. We have a node group set aside for jobs that will only run less than 24 hours. I think is that group. But we have node groups there, so if you want your job to run for 1 hour, it's not going to get shot down because someone has a job that needs to run for 7 days or something crazy like that. Again, shared resource, so we have these node groups. You could see which queue your job gets submitted to when you actually submit it. The system will actually say, okay, your job was submitted to short or something like that. Requesting a specific queue, the example there is if GPU nodes are needed. So there is a specific queue that has the node groups with GPUs. If you need to use a GPU, you typically in your job file specify that you want the GPU queue, and that tells Slurm, okay, only put this job on a resource that has a GPU attached to it. Batch queue policies are used to manage the workload and may be adjusted periodically. Yes, sometimes we adjust them as we see influxes of if everyone needs to run a 7-day job, obviously that's not going to work for everybody right off the bat, so we might implement some changes. Doesn't happen too often, but just something there to cover us, So viewing current queues, you're going to use Sinfo or Sinfo, stands for Slurm info. Sinfo sounds cooler though. This is a command that you can run from the terminal. So I'm going to, again, Control L, clear my screen and say Sinfo, and it's going to print out all the queues. So, okay, little side note here, queues are actually called partitions in Slurm, but queue kind of sounds like, when you think queue, you think of a line, or hopefully you think of a line, and that's kind of why we use the term queue. But the technical term in Slurm is called partition. So partition is queues, and here are all the queues we have. We have short, medium, long, GPU, VNC, extra long, staff, special. So you see this little star right here indicates that the short queue is the default queue, and we can see that this time limit is actually 2 hours. So it's saying for jobs less than 2 hours, they could be run here. And then it gives you some information on the current status of the queue. So you'll see there's a lot of overlap here. That's because a lot of nodes are in multiple queues. They're parts of multiple partitions. Again, we do that so if not a lot of people are submitting jobs in the short queue, we could use those queues. We can use those nodes for the long queue, the medium queue, or something like that. But these columns right here tell you the exact, the amount of activity there is. So in this column, this is organized by available, idle, offline, and total. So 251 nodes are available in the short queue. Only 2 of them are idle. 3 of them are offline for some reason, and 200, which gives us a total of 256 nodes. And then remember, the node is the computer, and you could kind of zoom into the computer itself and see how many CPUs there are on the computer. So breaking it down by CPUs, we have 500 and 5,000 available, 1,100 idle, 84 offline, and 71 total. So yeah, it kind of zooms in a little bit, gives you some more granular detail there. You might ask yourself, what's the special queue? If you have a job that doesn't really, that needs special attention for some reason, maybe it has a unique resource request that typically wouldn't get filled out, just kind of being thrown into the Slurm ecosystem itself. You can send us an email and we might be able to set up a time for you to run on the special queue. We have that there because there's sometimes some jobs don't really fit into the cookie cutter molds that we have assigned for the queues. So in cases like that, we have the special queue where you can request us to put your job there. Yeah, so you yourself won't be able to access the special queue, but if you email us and we work through a solution with you, we could drop your job there and it can run unimpeded. Okay, this is the moment, batch job scripts. Now again, we will be talking about scripts a little bit more this afternoon in the actual Slurm class, but because it's so key and integral to the use of Grace and Terra, we're gonna start covering it here. So this is a sample job script. These job scripts are available on our wiki, A&M, tamu.hprc.edu/wiki. You could find batch job examples. If you're new, I recommend you start by copying and pasting the examples on the wiki, putting them up on Grace or Terra, and then just kind of running the examples that are already there. You probably won't ever have to write your own job script because we have these examples here. You could just take them and modify the parameters and yeah, tweak it to fit your job. So what does the job actually look like? It looks like this. At the very top, we have the shebang, the bin bash. This is saying, hey, use the bash shell, because we're using a bash shell to submit this. So we want to run these commands as a bash shell. All the stuff beneath that, these capital hashtag S batches, these are called directives. Well, the technical term is called Slurm directive. They're your batch job parameters. So they describe your job to the job scheduler. This first group here are the necessary job specs. They set the environment, they set the name, they set the time, they tell how many cores you want to use, how much memory you want to use, and then it says where to put the output. So your job needs these to run. Beneath that, we have the optional specs. These optional specs are things like the account to charge. If you only have one account, you don't have to set this, but if you want to charge your professor's account, because remember your professor can give you SUs, if you want to charge your professor's account and not your account, you could specify that using this optional specification. And then you can also optionally opt to receive email updates when your job starts running and finishes running. You don't need them. In some cases, if you're doing a big job, your job might not start running immediately. It might take a few hours, so you want to submit it and then get an email notification when it runs. So you don't have to sit at your computer all day and just refresh and see if it started running yet. But after the job specifications, after all these capital S batches, these regular lines down here, this looks like stuff that we typed into the command line because it is stuff we typed into the command line before. You put the commands that you want Slurm to run directly beneath all of these S batch directives. So in this case, this job file, Slurm is going to read all of these parameters up here. It's gonna grab the resources that fit this job, and then once it grabs those resources, it's gonna run these commands right here on those resources. In this case, this is just gonna run on one node because we see one task, which is one CPU for and 2 gigs of memory. Very, very small job, and it's gonna type in for us on our load Python 3.7.0 until 2018, and then /myprogram.py. So you'll notice that you have to load the required modules. Even if you load the module in your shell, you need to document the steps that you took to create the environment inside the job script. So if you did not load Python 3.7.0 and you just said /myprogram.py, it's gonna run. It's gonna run with whatever version of Python is on the node at the time. You want to be very specific and recreate the environment. So always module load, the same module loads that you need to run your job from the terminal, you need to include those in the job script. So important batch job parameters, these are basically all the parameters that we saw at the very top. These right here, and then necessary. The first two, double dash export and double dash get user, these initialize the job environment. So they take a lot of your path from when you submitted the job, and it copies that environment to the compute nodes where your job will actually run. So it's actually going, like, your job is going to run on a different computer than the one that you submitted on. So these first two lines, don't touch them. They initialize the job environment. Beneath that, we have the time. Double dash time equals hours, minutes, seconds, seconds. That's the wall time for the job. Now the wall time is important. It's an important parameter. It's the limit for your job to run. So if you tell your job to run for 1 hour and then 1 hour comes, Slurm will kill your job at 1 hour. It's not going to run past your wall time. So you have to kind of estimate what your job will run for, how long your job will run for. You always want to overestimate how long you want your job to run for, because you will get refunded the SUs that your job does not, or you will be refunded the SUs for the time your job does not run. For example, if I submit a job for 3 hours, 3:03:00:00, so just 3 hours flat, and my job runs for 1 hour. When I submitted the job, I was charged for 3 hours of time, but because my job only ran for 1 hour, I get refunded those 2 hours worth of SUs that my job didn't use. So it's always better to overestimate than to underestimate, because the last thing you want to happen is your job to be running for 2 hours and 50 minutes, and then at hour 3, your job dies because it didn't have enough time to complete, and you have to go back and resubmit your entire job because you have incomplete results. Always overestimate. It's better to get the refund after the fact. Beneath that, we have end tasks. End tasks is the total number of tasks for the job. Tasks in Slurm talk is cores. So on Terra, we have 28 cores. On Grace, we have 48 cores. So the number of tasks, tasks per node, which is what we should be the item beneath that. So end tasks equals the total number of cores you want your job to use. And then end tasks per node specifies the maximum number of cores to allocate per node. So this is where you want to remember that Terra has 28 cores per node and Grace has 48. So this value right here, end tasks per node, on Terra can never exceed 28, and on Grace can never exceed 48. Beneath that, you have the memory values. So double dash mem equals, and then you could specify a value either in megabytes. You use the big M for megabytes or the big G for gigabytes. I recommend saying, I recommend always saying gigabytes because, well, there's really no reason to not use gigabytes. You're specifying memory per node. So if you said 20 Gs, you're saying, okay, I want this job, I want each node that this job runs on to have access to 20 gigabytes of memory. So these parameters right here are what AMS, which is our billing system, reads to charge you your SU. It's going to look at double dash time. It's going to look at double dash end tasks, and it's going to look at double dash mem. It uses those 3 parameters in that formula to calculate your total SU cost. So yeah, that's where SUs come from, and these are the important Slurm parameters. Oh, question.
This one may be dumb, but the account one, how we know our account?
Oh, so the question was, how do we know the account number? So in reference to this right here, this optional specification. Now it's an optional specification because when you have an account, that account is set as your default account. So you can omit this line, this double dash account line, and it's going to charge your default account, which is, you typically only have one default account. Like you only have one account. Yeah, so if you don't want to charge your default account, you want to charge another account, you can see your accounts by saying, I'm going to Control L to clear my screen, my project. When you say my project, it lists all of the project accounts that you have access to. So I have 2 accounts here. So I have 2 accounts, both with 5,000 SUs, and both under my my PI. So it's this number that you would take right here, Command C, Control C, and then paste this into your job script as right here, double dash account equals, and that's where it's going to get charged. The reason I can show you guys my account number and be fine is because you only have access, you can only charge accounts that you see here. So if you guys put one of these numbers in, you just get a permission denied error. So you can only charge accounts that you see listed under your project accounts. You could list your project accounts with my project. Good question. We have a question in the chat. Oh, okay. Yeah, we have a video on accounting. Okay. Good questions. Okay, mapping jobs to cores per node on Terra. So this is how you divide your job up across multiple nodes. It basically comes down to the combination of two parameters. Those parameters being n tasks, which gives you your total number of cores, and then your tasks per node. Do we have, just double check, make sure. Oh, we can make sure. Okay. The combination of these two parameters will help Slurm determine how many nodes you want to use. There is an actual explicit command for how many nodes you want to use. Okay, actually, let me take a step back and say this list right here is not an exhaustive list of all the parameters that you can use a Slurm. There's a whole lot of them. There's so many of them that you could really fine tune your job. If you're really so inclined, one, attend the Slurm primer or short course after this, and two, Google the Slurm job parameters. Like you can find the actual document that is written by Slurm that has all the parameters there. There's a whole lot of them. We try to kind of scope it down to only include the ones that you need to kind of understand what's really going on, which boils down to these. But yeah, this is not an exhaustive list. There's a whole bunch of other parameters too. So in our case, these two parameters right here are what we're going to focus on to control how many nodes we use. So in effect, how parallel we want our job to run. So example A, n tasks 28, tasks for node 28. So we take the total number of tasks, which is 28, divide that by 28, which gives us 1, and we're using one entire node. So that's kind of illustrated in this example right here. In example B, we take 28 tasks and we say tasks for node equals 14. So now we've split that 28 total cores across two different nodes. So now in example 1, each core just has to communicate with each other over the motherboard. In this case, now we're using interconnect to communicate between these nodes. In most cases, I guess, and sometimes you don't have to necessarily, but in most cases now you'd split your job up and then have these nodes communicate with each other to split up the problem. And then in example C, we do the same exact thing. We say 28 cores, but we're going to split it up even more and say 7 tasks per node. So 4 compute nodes, so 4 individual computers, 4 servers on Terra are running 7 of your processes each, and then they're all communicating back with each other. So this is the principal foundation of parallel computing here. The question stands then, why not just separate my job until it's like 1 core per node for 28 nodes? And the reason you wouldn't want to do that necessarily is because eventually the overhead of communicating between nodes exceeds the benefit that you get from splitting your job up. So it becomes costly to actually communicate between nodes. It's super efficient for CPUs to talk to each other when they're on the same motherboard. It becomes magnitudes less efficient when you have to run that communication over an interconnect. Even if you have really high speed interconnect like OmniPath or something like that, it ends up being pretty difficult. Did you have a question? No, okay. So yeah, that's like the fundamental idea of parallel computing. So you control how many nodes you want to use by saying tasks per node in SBatch. You do the same thing on Terra, on Grace, sorry. Just remember that you have 48 instead of 28 cores available on each node. I didn't illustrate that here because 48 cores in a little square gets kind of hard to see. So it loses its punch, I think. But that's the idea. Okay, so now we talked about cores, let's talk about memory. So you specify the memory request based on the memory per node. That's this ~mem value that we said earlier. On Terra, most nodes have 64 gigabytes of memory. On those 64 gigabyte nodes, the usable memory is at most 56. So although we say 64 gigs, it's kind of a lie. You actually only have about 56 gigs of free memory. And that is because the operating system itself, CentOS, and Slurm, the job scheduler, need to reserve memory for themselves. They have to run on something. So they need the resources on the node to kind of facilitate the task that they do. So for that reason, they reserve a little bit of memory, which comes out to like, what, 8 gigs or so per node, which leaves you with 56 free gigs of memory that you can use. So that puts the per process, AKA the per CPU memory limit at around 2,000 megabytes, which is a little less than 2 gigs for a 28 core job. So kind of tight. On Terra, also, we have 128 gigabyte nodes. So same deal there. The usable memory is at most 112 gigs, which puts the per process memory limit around 4,000 megabytes, which is a little bit less than 4 gigs. Do the math. Remember, a gig is 1024, not 100 megabytes. So, okay. Now Grace. Grace has larger memory nodes. Same deal, specify the memory in the same way. Double dash mem equals X gigabytes. Replace X with the amount of gigs you want to use. On Grace, most nodes have 384 gigabytes of memory, a large step up from 64. And the usable memory there is going to be about 360, which puts the per process memory limit to the per CPU for an entire node is going to be about 7.5 gigs for a 48 core job. There are also 3 terabyte nodes on Grace. Yeah, that's 3 terabytes of memory. That's kind of crazy, right? But on those super large memory nodes, the usable memory is at most 2,900 gigabytes. It's like 2.9 terabytes roughly, which puts the per CPU memory limit at a whopping 37 gigs-ish, somewhere around there. I didn't include this squiggly there. I don't remember that's exact math or what, but yeah, that's a whole lot of memory. But yeah, that's kind of a niche case too. So key takeaway, the nodes have a little bit less memory than they kind of advertise because the operating system and Slurm needs to exist. So they kind of take up a little bit. Okay, let's have a really quick pop quiz. This is the only one I included. So how many nodes is this job requesting? So I'll give you a hint. The items that we're looking at here are n tasks, remember, because n tasks is how many CPUs we're using. So we're saying 80 CPUs and 20 CPUs per node. So we're not explicitly asking for an amount of nodes, but with a little bit of, exactly, there you go, 4, yeah, right. The answer is D, 4. We're implicitly saying 4 nodes. So Slurm will read this and say, okay, I'm gonna reserve 4 different nodes for you and give you 40 gigs of memory on each node. And you're gonna have access to that for 48 hours or 2 days. Good job. If I had a t-shirt, you would receive one, but I don't have one, sorry. Okay, job submission and tracking. So after you submit your job, you can submit it. I think I go over some of these commands. Okay. So to actually submit your job file, you say sbatch. In the job script file, you say sbatch to set a directive from your actual terminal. Oops, that's not what I want to do. This is what I want to do. From your actual terminal, you say sbatch like this, and then some file, and this submits the job to Slurm. Some file doesn't exist, so Slurm says, hey, we had an error, unable to open some file. It doesn't exist. I just kind of made that up right now. Control L to clear my screen. You can view the status of your job with SQ. SQ minus, well, let's see. SQ itself shows you every single job that's running. It's kind of useless because, you know, who cares about other people? So if you only want to see your jobs, it's SQ minus U and then your net ID. If I do it for myself, I don't have any jobs running right now, but in a second I will, and you'll be able to see it there. So SQ minus U shows you your jobs. And I guess you could run SQ on your classmates to see if they're actually doing their jobs. How to kill a job? That's S cancel. S cancel and the job ID. Where do you get the job ID? Well, the output here, it's kind of weird looking because I have like the text so big. But when you do SQ the first column is the job ID. It's like all these are job IDs right here. When you run it on yourself, like SQ minus U, you'll see it right here. It'll be real simple. But SQ gives you the job ID, and then S cancel with the job ID kills the job. If you try to kill your classmate's job, one, you're not a nice person for doing that, and two, you can't do it anyway because you can only kill jobs that you've submitted. So you can only S cancel jobs that are owned by you. Then we have S account. S account shows information for a job. It shows like SU usage. You kind of really won't use S account. That's kind of for showing historical. That's more like for like if your professor wanted to track all of the jobs that his students have been running, you kind of use S account. We include it here because it is a job submission tracking, a job tracking tool. But new users, you typically won't use S account. The ones you will probably use are LNU, PEstat, and Ceph. I think I have slides on each of these later on, but these basically list the node utilization. And I don't know what PEstat stands for. LNU means list node utilization. I'm not sure what PEstat stands for. It's a tool that shows the resource usage for a running job. So use LNU on a job that's already finished. You use PEstat on a user. So I'd say PEstat minus U Dylan, and it would show you the resource usage for jobs that I'm currently running. And then Ceph shows you the CPU and memory efficiency for a job. So just because you tell Slurm to reserve the allocation, the resources for you, doesn't mean that your code's going to use it. That's up to you. So you have to write the code so that it uses the resources. You could ask for 3 terabytes of memory, and then just run a little Python script that says hello world, and it's going to use like, I don't know what, like not anything. And then you wouldn't be charged for it because you'd be refunded the difference, but you just waited a long time to get run on the 3 terabyte nodes when you didn't need to do that. So you could actually check the CPU and memory efficiency with Ceph, and you give Ceph the job ID. Again, you find the job ID from SQ. Oh, I blew past our break, but we're right towards the end, so I think we can just we're just gonna power through it. We're right here. Job environment variables. Do we need to talk about these? I don't really think we do. We talked about the path. The path is where all the executables are. The LD library path is the list of directories where libraries are found. That gets set automatically. You don't really have to worry about that. A Scratch, probably the one that you're going to want to remember. That's just a shorthand for your Scratch directory. So $Scratch will point to your Scratch user net ID. In my case, Scratch user Dylan. In your case, Scratch user whatever your net ID is. And then Slurm has some job environment variables, which we really won't go into too much. But I guess the important one here is tempter. Tempter is a variable that points to /work/job.slurm job ID. So it's gonna each compute node that your job runs on has a local temp directory. It's local to each compute node, and it's about 850 gigs. So if your job needs to store files in a space temporarily, and you won't need to retrieve them later, your job can use tempter, that variable, to store files, then retrieve them as it's doing its work. It'll get wiped when your job leaves it. Or I don't know if it'll get wiped, but it's not for storing stuff like your Scratch. It's for your job to use while it's running. Yeah, so you shouldn't use tempter for software that has checkpoints to restart where it left off. If you're checkpointing if your job has software that's checkpointing, the checkpoint should be written to your Scratch directory or your home, I guess, if it's really small. Okay, so I think there are 5 exercises. We're going to go through 2 of them, and then I'll leave the other 3 for people who want to explore on their own, and then that'll be it. Yeah, so tempter gets wiped at the end of a job. Thank you, Lisa. Okay, so the actual exercises, if you want to follow along, are I'm going to Control L to clear my screen and then make it bigger again. And I will move this up here so we could see the slides too. I'm going to move to my Scratch directory, and then I'm going to say cp -r/scratch/training/intro to Terra. Intro to Terra, and then period. So this copies the training files into my directory. And so now I'm going to move into intro to Terra. I'm going to move into batch examples. And I'm going to show you guys how to submit a job. So in here, I have a couple job files. I have example01.job. So let's, I'm going to go ahead and open that file. So I'm going to say vim. Actually, I'll just cat it out for simplicity's sake. So when I print the contents of this is what the job file looks like. So it's just a text file that we see here. I'm gonna zoom out a little bit so we can kind of see it a little bit better. Hold on, sorry. Okay, so at the top we see the shebang, and then we see the environment variables. So here's the sbatch export, sbatch --get user. Then we see the necessary job specs. We see that this job is going to be named example1 _ environment _ variables. We see it wants to run for a total of 2 minutes, a whopping 2 minutes. And then we're asking for 1 core and 2000 megabytes, so a little bit less than 2 gigs. And we're saying we want to name the output, --output specifies what we want to name the output. We're saying output.ex01.environment variables.%j. %j is a variable for the job ID. So I don't know what this job ID is going to be before I submit the job, but this %j will get turned into the job ID that gets assigned to it. And then here are the optional specifications. So a single hashtag will be read as a directive. A double hashtag just comments it out. So you see double hashtag sbatch. That means that these lines right here will be these will be commented out. They will be ignored by Slurm. So in effect, we're not using any optional specifications. We're only using these necessary ones. And then beneath all that, we have the actual commands that will be run. So this job will run echo load module Intel 2018B, and it's going to actually load the module. And then once it loads the module, it's going to echo. Echo is a Linux command to just kind of print to the terminal. So we're saying, or print to the standard output. It's going to print to the standard output the user value, the value that's in the user variable, the value that's in the PWD variable, and it's printing the value that's in all these variables. So let's just go ahead and submit this job. Say sbatch example. Might be hard for you guys to see it. Sbatch example1.job. And now that I've submitted the job, Slurm says, okay, we've submitted batch job 9052628. That's my job ID. Your job has been charged as below. What project account did it charge? It charged my default account because I didn't specify one, an account to charge in the job file. That account had 4,955 SUs. And this job cost 0.03 repeating SUs because it was 2 gigs of memory for like 2 minutes. So like super, super small. So if I do LL again to list the contents, I can see now we have the output here. So this file got created when I submitted the job. The job was submitted, it ran, and it got the output here. So I'm gonna print the contents of this output with cat output example1. And it looks like a whole bunch of mess because at the very bottom, we printed 2 variables that are very messy, which is path and LD library path. So it did exactly what we told it to do. It echoed load module, and then it actually loaded it. It printed the contents of these variables. So the user variable is Dylan, the PWD, which is the work directory, is where I submitted the job from. The Slurm job ID is the job ID right there. The submit directory is where I actually submitted the job from, and then scratch and all that stuff. So that's the idea. I'm gonna RM to remove this output. I did want to show you guys. I think example 2 will hang. So let's show you guys this one. So if I sbatch, first off, let's take a look. Let's vim or cat Control L to clear my screen. Cat example2.job. Now this one's not going to hang. Oh, it might actually. I'm going to sbatch example2.job. So I'm submitting this one, and I'm going to immediately say SQ dash U Dylan. And so now I see that I have this job right here. Here's the ID. Here's the name of the job. Here's the user. It can run in the short, medium, or long queue, and it's pending. And now it's running. I SQ'd again. I can see that it's running. And if I SQ one more time, it's still running. It should run for 20 seconds, I think. We had that for 1 in 20. Let's see. There we go. Yeah, ran for 20 seconds. And now if I do LL, now I can see the output here. Let's go ahead and cat this output. And I see the output. So the output was a bash loop that just printed, it counted 1 to 20 every second. That was just to kind of show you a job that would take that long to run. But that's basically that's the idea of submitting jobs. You write a job file. You could either write the job file here on Terra or Grace, or you could write it on your computer and then upload it the way I showed you through the portal. You SBatch submit it. You're gonna see it in SQ. Once it runs, the output will be typically in the directory where you submitted it from. Let's see. I think that was basically all I had. These we're not going to go over. So I talked about this already. Checking your SU, your service unit balance. You're going to use Control L to clear my screen. My project itself will show you your allocations and your balances. So as a student, like I said, you'll have 5,000, and then once you have your 5,000, if your professor applies for a startup and lists you as a student on his startup, you'll have another account just like this, and then you could specify this account inside your job file to charge that account. If you want to change your default account, it's my project -D as in default, and then you give it the account number that you want to change to your default. Pretty simple on that one too. Hit enter. Okay, and that says my default project account is now this fiscal year 22 account. So my project again, and I see that yeah, default is now Y down here for yes. Insufficient SUs. Oh, I did talk about this. So there's a bonus assignment. Modified job files that the requested SUs are too much for your account. So I'm not gonna make y'all do that for fear of accidentally draining all your SUs. But if you submit a job that requires more SUs than you have, SBatch will give you an error, and it'll look like this. Your account's balance is not sufficient to submit your job. It shows the account number, and then shows your balance, and then shows how many you requested. Like I said before, if you need more SUs, you have to ask your PI, so ask your professor or your advisor or whoever you're researching for to transfer SUs to your account. They transfer those SUs to your account from their own startup account, which is an allocation that they apply for. The startup allocation looks a lot like the basic allocation. It just has a few more questions and requires a little bit more documentation. Other batch examples are shown right here. This is a very simple job. This is, you can't really see it, but time is 1 hour and 30 minutes, 1 core. This is a serial job. A single node multi-core. So we're on 1 node here, and we're saying 1 node, 8 cores and 8 gigs. So this little diagram up here. These files just kind of demonstrate that you could switch your job up and divide it across multiple nodes or keep it on 1 node. Multi-node, multi-core. So this job right here is going to run for 1 day, 12 hours, use 8 cores total, and have 2 cores per node. Does this make sense practically? Not at all. It's just showing you that you could divide your job up like this. So again, N tasks and N tasks per node are what you use to imply the amount of nodes you want to use. Unless you want to explicitly say _ nodes, that's fine too. However, it typically makes more sense to kind of implicitly say how many nodes you want by doing the math here. And then a GPU job. And here we're saying 1 core, and these 2 lines down here specify the GPU option, we're saying gres, which means we want to reserve a specific resource. That resource is a GPU. Specifically, we want to use one GPU and then throw us in the GPU partition. So the nodes in the GPU partition are going to have a GPU resource available, and you're going to request one of them. And if you're paying really close attention, you'll notice that you're going to be charged 28 SUs. Why is that? The reason they're going to be charged 28 SUs is because if you're on a GPU node and you request one GPU, you end up being charged the entire node. So you get charged for 28 cores, regardless of if you use them or not. So if you're requesting GPUs, as it stands right now on Terra and Grace, you want to just use the entire node. That's a limitation that we have with Storm right now. We're working on fixing that so that you only get charged what you get, what you request. But as it stands right now, if you're requesting GPUs on Grace or Terra, you might as well request all the CPUs because you're going to get charged for them. Okay, and then these last 3 slides are list node utilization. This is how you'd see the node utilization. You give it the job ID, get the job ID from SQ. Slurm updates this information every few minutes. So on a job that's running, you'll see information like this. It includes where the job is actually running. So this line right here, this column, TNXT, and then some numbers. These are the actual host names, the actual computers that are running your job. Then you see the CPU load, how much memory is free, how much memory is free, how much memory is available total, and then the CPUs in the same vein as the queues in available, idle, offline, and total. CPU load is not the same as percent utilization. For that, you could you'd probably want to be looking at Ceph. So a Ceph is another tool that you give the job ID to, just SEFF and then the tool, SEFF and the job ID. PEstat, you give the username. So it lists node utilization across all nodes for a running job. So you would say PEstat minus U Dylan, and you'd see all the jobs that I have running and their CPU load, as well as memory size. PEstat is a little bit nicer than LNU in my opinion, because it's got colors to it. So it shows you what's low utilization and what's good utilization, as well as what's ideal. So ideal is going to be white, good is going to be purple, and if your job has reserved a core but it's not really using all that core, all that CPU, it's going to come up in red and say, hey, you requested it, but it doesn't really look like it's using it. So maybe you can either, if that happens to you, you're going to want to look at your code, revisit your code and see what's kind of going on there, or maybe reduce the amount of CPUs that you're requesting, because you might be requesting too many resources and not really using them. Other types of jobs, MPI and OpenMP. MPI jobs and OpenMP jobs are message passing interface jobs. Those are for big parallel jobs. That's when you're going to have special libraries that help facilitate the communication of your CPUs across multiple nodes. You have visualization jobs. That's the portal. That's where you go to the portal. You say interactive apps, and you run like MATLAB through the GUI or ANSYS through the GUI, stuff like that. Jupyter Notebook through the GUI. Large number of concurrent single core jobs. So you have tons of really small single core jobs. You could use Temu Launcher. We have a wiki page on it. It's useful for doing just that, running many single core jobs concurrently across multiple nodes. It can be used with serial or multi-threaded programs, making it very versatile. It distributes a set of commands from an input file to run on the cores assigned to a job. It can only be used in batch jobs too. So can't use it from the login nodes. So if that sounds like something that you need to take advantage of, concurrent single core jobs, Temu Launcher is the way to go. There's a wiki page for it. If a Temu Launcher job gets killed, you can resubmit the same job to complete the unfinished commands in the input file. Okay, and I leave y'all with that. So if you guys need any help, first I recommend going to the FAQ and then the user guide for the clusters. So in other words, go to the wiki. If you can't find your answer there, feel free to email us at help@hprc.temu.edu. It's managed by a ticketing system, and there's a group of us who work at the help desk, so we will respond to your email. You can also give us a call. I think our phone number is on the website, but we'll be here. We're in Blocker now, I should mention that. So our old help desk used to be in Henderson. We're kind of split between Henderson and Blocker right now. So if you go to this office in Henderson, no one's gonna be there, or no one should be there. I think a few people might be there, but we're mostly in Blocker now. So we're in Blocker. I forget the room number, but if you go to the second floor blocker, you'll see the signs that say like HPRC this way. It's on the second floor blocker on the left as you walk up the stairs. Our help desk is there. If you send us an email, just kind of include this information. What cluster are you using? What's your username? What's your net ID? What job IDs are applicable? Where's the job file? That sort of stuff. That really helps us cut down the time to kind of get you an answer to your question. Yeah, that's all I've got. So thank you guys for coming to this first short course.